The concept of skew will become much more important subject-wise as we begin to discuss the topic of the normal distribution and what qualifies a distribution as parametric. In this video, we'll discuss the definition of skew and tests which can be applied to determine whether your data is skewed. And we'll also discuss the topic of percentile as well. So the definition of skew in probability and statistics, skewness is a measure of the asymmetry of the probability distribution of a real valued random variable about its mean. The skewness value can be positive, 0, negative, or undefined. So here's some data which we collected from a particular phenomenon. So something's occurring somewhere, and we either go out with our clipboard or send someone from our group, our research group, to go and collect data as it pertains to this phenomenon. And this is what we receive back as it pertains to sample observations from the phenomenon. So we have to get this data into R. And we're going to do that with a data vector. So I'm going to move to R now, and we'll go between RStudio and our slides. So here is RStudio. And as you can see, we have our data elements that we're going to utilize to create a data vector. So to create a data vector, which contains the elements which we like to have it contain, we have to use C, open parens, we put all the values in each element, and then we close the parens, make sure that the element values are separated by a comma, except for the last value. You don't want to have a comma there, or the code won't execute correctly. So we're going to close that, make sure all of our values from our sample series are in there. Make sure we have the letter C. And then it's X less than sign dash. And the code will be in the video description, although I'm not sure if I can use a greater than or less than sign in YouTube description code or the YouTube description of the video. There's a restriction for that, but I'll do my best. If I leave this off, you'll have to make the change on your own, but I trust you can do it. Anyway, as you can see, if you run this bit of code, the value of X, vector X, is now present where it wasn't before. So we need to do a couple of tests and analysis methodologies to determine whether or not we can make the distinction as to our data being skewed or not skewed. So if you're in a statistics course, Stat 101, or in the classroom, they probably have told you to look at skewness, kurtosis, histogram, etc. And we're going to look at some of those method applications, but really in the real world for your research, if you're a researcher, the only real application that you need to utilize is the Shapiro-Wilk Normality Test. This is the tried and true right here. And the Shapiro-Wilk Normality Test presents us with this hypothesis. Our null hypothesis is the data does follow a normal distribution, and the alternative hypothesis is the data does not follow a normal distribution. So why don't we go ahead and let's perform this analysis right here by applying the Shapiro-Wilk Normality Test, and that's Shapiro.test, and then whatever the name of our data vector is within parentheses there. So let's go ahead and do this. So as you can see, our p-value here is 0.3298, which is certainly far and above the typically assumed alpha value of 0.05. So if the P is low, the null must go. In this case, the P is not low, so the null doesn't go. So that being said, assuming an alpha value of 0.05 and applying the Shapiro-Wilk Normality Test, no statistically significant departure from normality was found. Okay? So we failed to reject the null hypothesis. The data does follow a normal distribution. And let me go back to our slides here. Let me get the slides back up. Here we are. So this is the hypothesis for this particular test. This is our output if it was difficult to view on the prior screen. And again, we failed to reject the null hypothesis because our p-value exceeds the alpha value of 0.05. Now, if you're stuck in Statistics 101, you probably have to create a histogram to visualize the data. Now, I'm against this because this typically creates, go ahead, do whatever your instructor tells you to do. Or if you're doing research and someone in the research consortium or in your dissertation committee informs you that this is a necessary step which you must undergo, go ahead and do it. But there's often confusion for some individuals as it pertains to histograms and probability distribution graphs. And we'll talk more about the graphical depiction of probability density in later lectures. However, let me just generalize the concept right now. Histograms, and this was also discussed within a prior video in the playlist, histograms are graphical depictions of events which have previously occurred. Generally speaking, that's the definition. Probability distribution graphics are illustrations of events which have yet to occur. All right? So assessing the potential probability of event, not graphing the frequency of a particular event, prior occurrence, that is a relatively decent definition for the graphical display of a probability distribution. So again, histogram, events which have already occurred, the frequency, probability distribution, graphically displayed, is a way of viewing and graphing probabilistic outcomes as they may occur in the future as it relates to which you believe is the summary of the underlying phenomenon. So in this case, if we were to apply the hist function, let me go back to R, to our data vector, we receive this histogram display. And we're looking for a display as it relates to a histogram. And again, it's not a perfect way to do it. But if you're in a class, you want it to be as bell-shaped as possible. So you would like to have this be a perfect symmetrical hump. Just goes straight up into a bump and then comes right back down. Like a camel. If a camel had one single perfect hump. You want it to max out in the center and then come down gently into a perfect singular symmetrical bump. And this looks like it's about close enough. If we have no other tools at our disposal and we have to use a histogram, well, this data doesn't look like it possesses that much of a skew. Now, as it relates to skewedness itself, well, there's a test for that as well. And again, we're testing the skewedness of data, but there's also a skewedness as a definition or an attribute definition of the data. So if you needed to test for skewness in R, you need to have the moments package successfully downloaded and installed. And there's a video on how to do that, how to install R Commander, and the R software. Go ahead and watch that if you need help with packages. In any case, you would just click packages over here, click install, and then put moments as the package which you'd like to install in the appropriate field, install that, and then you have the option of either clicking within the packages tab, this box here next to moments, or you could just type library, open parentheses, moments, close parentheses, run that code, and that will enable the appropriate moments package, which will allow you to test for skewness. So with this package downloaded and enabled in our session, let's go ahead and test our data vector for skewness as the definition of skewness is concerned. So in this case, our value is negative 0.07607,462. So we could say, perhaps round that to, I don't know, negative 0.08. But that doesn't tell us very much unless we look at the appropriate definition here. Let's take a look here. Go back to our slides. So here's our output if you were unable to view it due to how tiny it was on the prior screen. So our value was 0.08. So with that, we would assume, because it's between the value between negative 0.05 to negative 0.5 to 0.5, that would be perfectly symmetric. Moderately skewed would be between negative 1 and 0.5, or between 0.5 and 1. And highly skewed is values less than negative 1 or greater than 1. Well, ours was 0.08, negative 0.08. So negative 0.08 would be here, negative 0.08. All right. So we would use, if you're in a statistics course, all of the tools that you have at your disposal, whether it be this skew, we would look at skew as an attribute. We would look at kurtosis, perhaps, which we're not going to look at in this particular lecture. We would look at the histogram. But if you're doing real research in the real world, you would only look at the Shapiro-Wilk Normality Test. But anyway, all of the values which you receive for as it relates to each test should be enough in tandem to determine whether your data is skewed or otherwise. And that's important, again, because we'll later determine the difference between parametric and non-parametric data. And understanding that difference is important because it will determine what methodologies are appropriate for the underlying data which you're observing and the test which you are utilizing. So here's just some general observations as it relates to data. If the data has a left skew, and we're looking at a probabilistic distribution visually displayed. A left skew would mean the bump, again, this is a probability distribution. A left skew would mean the bump is on the right. So I know that this is contradictory, but left skew means bump on the right. All right, bump on the right. A right skew means bump on the left. And a perfect symmetric distribution, which you'll really never encounter outside of a textbook or outside of the definition of the term, means that the data is a perfect bell shape, perfect bump, normal curve. This side on the left perfectly corresponds to the side on the right, and the highest most point is in the center. All right, so generally, if the distribution of data is skewed to the left, the mean is less than the median. And generally, if the distribution is skewed to the right, the mean is greater than the median, generally speaking. But remember, right skewed, left skewed, don't get confused, all right? Bump is on the right, it's a left skew. Bump is on the left, it's a right skew. It's also important to note that data can possess a skew and also adhere to the assumptions of a parametric distribution. What this means will become more evident as we go through the playlist, but essentially data doesn't always need to be perfect as it pertains to the underlying assumptions, which are necessary for determining what test methodology is appropriate. So now we're going to change gears a bit. Think of this as sort of a double feature. We're now going to talk about percentile. Many of you probably have, at one point or another, encountered percentile, either as a definition or just in general throughout your daily existence. This was big with standardized tests where you stand percentile-wise amongst your peers. It's also utilized if you go to the doctor and they do your height and weight, they can sometimes determine based on your age and your gender where you are percentile-wise as it relates to, again, your peers who are similarly observed. But in any case, the definition of percentile. In statistics, a percentile is a term that describes how a score compares to other scores from the same set. Again, we're doing comparisons here. This is very important. While there is no universal definition of a percentile, it is commonly expressed as the percentage of values in a set of data scores that fall below a given value. Again, no universal definition. However, we're going to go over how it's commonly defined. So if you're in a situation where it's life and death and someone is giving you a percentile, make sure you understand the underlying methodology which they're utilizing. We're just going to use a general methodology here. And in most cases, percentile is, illustrating something in generalized terms, not in a manner in which someone's life could be permanently and adversely impacted. So we're going to do this little example here in R again. We're going to test this data and we're going to assess the percentile and the quartile as it pertains to the data elements. So we're going to create a data vector. And again, this is the code for a data vector. I'm going to try to put this in the video description, but YouTube is funky when it comes to video descriptions and greater than or less than symbols. So if this is missing, you got to put that on yourself, all right? All right, so let's quickly do this in R. Here we are. All right, and if you ever need to clear the console, it's Control L. Control L clears the console. All right, So here are our data elements, and we're going to put those into a new data vector x. So this x vector will replace the one which previously existed. We're going to overwrite that. So here is our data vector with each corresponding element. We're now interested in the quartiles. And remember, we went over this in the lecture on general R commander utilization. Well, if you want to do this outside of R commander, if you want to find quartiles as it relates to a data vector, this is the code that you would utilize. It's the quartile function, the vector, then the quartiles which you're interested in determining, and then type equals 1. So let's go ahead and perform that function. And here we have the quartiles for this data vector x, 0%, 25%, 50%, 75, 100. And these are the corresponding values for each. But let's say that we're only interested in the percentile of a single value. That value being 5 as it relates to this vector. So if you have the score of 5, or if someone receives a score of 5, or just generally, which percentile would the value of 5 generate or indicate as it relates to this data set? Let's go ahead. That's ECDF, open parens, X, close parens, open parens, 5, because that's the value we're interested in. So here's our data vector, value of 5. So let's run that. And we get the value of 0.5. So 5, as it relates to this data collected here, this data vector is in the 50th percentile. All right. If you were having trouble seeing that, this is what was going down. So again, it's important to remember that we're just doing a general description of the concept here. There are other ways to define the method which is utilized to derive percentile. Be aware of which one is being utilized, and if you're in class, be sure you know which one your instructor would like you to put into practice. So here is a example of what percentile is looking to illustrate. If we have a group of people, what percentile is the fourth tallest person in this group of 20? So here are our 20 individuals, and we're interested in the percentile as it pertains to height for this individual. Well, that would be the number of data points below. Okay. So there's 16 individuals below this individual, divided by the total number of data points. There are 20 individuals in general. And then we multiply that by 100. So 16 divided by 20 multiplied by 100 gives us the value of 80. So therefore, this individual falls into the 80th percentile as it relates to height. All right? So sometimes people can get confused by this because they think that, okay, well, if it's 80th percentile, that means that, it's a score, like it's a score on a quiz or something of that matter, like 80 out of 100 or something like that. But really what this is saying is that this particular individual is taller than 80% of their contemporaries. Therefore, they fall into the 80th percentile. Okay? If you want to test it, you can work through it yourself using the code. But in any event, that's it for this particular video. I know it's a longer one, but I appreciate you sitting through and stopping by. If this helped you out, please consider liking and subscribing, and have a wonderful rest of the day. Take care.